Welcome to this coding tutorial. Today, we will be exploring the problem number 995, minimum number of k consecutive bit flips. This is an interesting problem that challenges your understanding of array manipulation and efficient algorithms. Let's dive in and solve it step by step. In this problem, we are tasked with determining the minimum number of k-bit flips required to turn every element of a binary array nums into 1. A k-bit flip means that we take a subarray of length k and flip every bit in that subarray. All 0s in the subarray become 1s, and all 1s becomes 0s. If it's impossible to make all elements of the array equal to 1, we return -1. The input consists of a binary array nums, where each element is either 0 or 1, and an integer k, which specifies the size of the subarray we can flip. The output is an integer representing the minimum number of flips required or -1 if the task cannot be accomplished. The problem also specifies that the array can be quite large, with its length going up to 100,000 elements, so efficiency is key when designing a solution. Let's look at some examples to better understand the problem. In the first example, the input array is nums equals 0, 1, 0, and the subarray size is k equals 1. To solve this, we first flip the first bit, changing the array to 1, 1, 0. Then, we flip the third bit, resulting in 1, 1, 1. At this point, all elements are 1, and the total number of flips required was 2. So, the output for this example is 2. In the second example, we are given nums equals 1, 1, 0, and k equals 2. Here, it is impossible to flip the array to make all elements 1 because the last 0 cannot form a subarray of size k equals 2. Since there's no way to meet the requirement, the output is -1. In the third example, we have nums equals 0, 0, 0, 1, 0, 1, 1, 0, and k equals 3. First, we flip the first 3 bits, which transforms the array into 1, 1, 1, 1, 0, 1, 1, 0. Next, we flip the subarray starting at the 5th bit, flipping the 5th, 6th, and 7th bits. This changes the array to 1, 1, 1, 1, 1, 0, 0, 1. Finally, we flip the subarray starting at the 6th bit, which flips the last 3 bits, resulting in 1, 1, 1, 1, 1, 1, 1, 1. All elements are now 1, and the total number of flips required is 3. Thus, the output for this example is 3. To summarize the problem constraints and edge cases, the binary array nums can have a length ranging from 1 to 100,000, and the subarray size k is always between 1 and the length of nums. Each element in nums is either 0 or 1. Key edge cases include the smallest input size, where nums has only one element. If nums equals 0 and k equals 1, flipping is always possible, and the output is 1. In cases where the last 0 cannot be covered by a subarray of size k, the output should be -1. If the array already consists entirely of 1s, the output is 0 since no flips are needed. Finally, for large input sizes, solutions must be efficient, ideally operating in O(n) time complexity to handle arrays with up to 100,000 elements. To tackle this problem, one initial approach we could consider is the brute force method. The idea here is straightforward: iterate through the array, and whenever we encounter a 0, flip the next k consecutive bits. This involves manually toggling each bit in the subarray of size k. The steps include iterating from the start of the array up to the point where a k-sized window can still fit. If the current bit is 0, we perform a flip operation on the range I plus k1 and count that flip. However, if we reach a point where flipping is no longer possible due to the window going out of bounds, we return -1, indicating that the task cannot be completed. While this method is simple to grasp, its inefficiency becomes apparent with larger arrays. The time complexity is O(n*k), as flipping all k bits for each 0 results in significant redundant work, especially when flips overlap. The space complexity is O(1), since no additional data structures are used. However, this approach fails to optimize for overlapping flips, leading to unnecessary computations. An optimized approach improves upon the brute force method by leveraging a sliding window technique combined with lazy propagation. Instead of flipping the bits directly, we keep track of the cumulative effect of flips. The key insight here is that the state of a bit depends on how many flips have affected it. If a bit has been flipped an odd number of times, its value changes. if flipped an even number of times, it remains the same. To manage this efficiently, we use a sliding window to track the number of active flips currently affecting the index we are processing. This avoids the need to repeatedly toggle bits in the array, significantly reducing redundant operations. By focusing on the state of each index rather than performing direct flips, we can optimize the overall process. To implement the sliding window approach, we maintain a flip_count variable to track the number of active flips. As we iterate through the array, we determine the state of each bit by checking whether flip_count is odd or even. If the current bit needs to be flipped, we increment flip_count and mark the start of a new flip. At the same time, we ensure to end the effect of a flip when its window of size k expires, which occurs at index I k plus 1. If, at any point, we determine that a flip is necessary but the remaining portion of the array is smaller than k, the task becomes impossible, and we return -1. Finally, we count and return the total number of flips performed. This method significantly improves efficiency, reducing the time complexity to O(n), since each index is processed at most twice, once when it enters the sliding window and once when it exits. The space complexity remains O(1), as only a few variables are used to track the state. When comparing the two approaches, the brute force method is easy to implement and understand, making it a good starting point for smaller inputs. However, its inefficiency becomes evident with larger arrays, as redundant operations from overlapping flips result in poor performance. On the other hand, the optimized sliding window approach is much more efficient, taking advantage of the overlapping nature of flips to minimize redundant work. While it involves slightly more complex logic, the benefits of linear time complexity and efficient handling of flips make it the better choice for larger inputs. For these reasons, the sliding window technique with lazy propagation is the preferred solution for this problem, balancing efficiency and scalability. In this problem, we are tasked with transforming a binary array nums into an array where every element is 1. The operation we can use is flipping exactly k consecutive bits, starting from any index. Our goal is to determine the minimum number of such operations required to make all elements 1. If it's not possible to achieve this, we return -1. To begin with, let's understand the brute force approach. The intuition here is to iterate through the array and flip k consecutive bits whenever we encounter a 0. This ensures that we make progress toward converting all elements to 1. First, we initialize key variables, n to represent the length of the array and flip_count to track the number of flips performed. Then, we iterate from the start of the array up to nk, ensuring that any flip operation remains within bounds. This forms the foundation of the brute force method. When iterating through the array, the next step is to check for any 0 at the current index. If nums I is 0, it means we need to initiate a flip operation starting at index I. During this operation, we toggle all elements in the subarray I plus k, flipping 0s to 1s and 1s to 0s. After completing the flip, we increment the flip_count variable to record the operation. Once we've processed all possible flips, we validate the array by checking if all elements are now 1. If so, we return the flip_count as the result. However, if any 0 remains in the array after processing, it means it's impossible to achieve the desired state, so we return -1. An important edge case to consider here is when k is greater than the length of the array, as it would make flipping any subarray impossible, and we would immediately return -1 in such scenarios. This brute force approach highlights some key insights. Flipping k bits is a greedy strategy where we address the leftmost 0 as soon as we encounter it. This ensures that progress is made toward the goal. However, the inherent inefficiency lies in the repeated flipping operations, which result in a high time complexity. Some important edge cases to keep in mind include scenarios where k is larger than the array size, arrays that are already all 1s, and cases where a 0 persists because it cannot be part of any valid subarray. The core data structures here include the input array itself, which undergoes modifications during the flipping process, and a counter variable flip_count to track the number of operations. The key operations involve toggling the values in the subarray I plus k during each flip and performing a secondary validation pass to ensure all elements are 1. Now, let's analyze the complexity of this brute force approach. The time complexity is driven by the flipping process. For each 0 encountered, we flip k elements. In the worst case, this results in O and asterisk k operations, which can become computationally expensive for large arrays in values of k. The space complexity, on the other hand, is O(1), since we modify the input array directly without using additional data structures. To optimize this approach, we can avoid directly flipping the bits in the array by using a flip_ flag. This flag helps track whether a bit is effectively flipped without actually modifying the array. This optimization significantly reduces the runtime complexity. For instance, consider the example where nums equals 0, 0, 1, 0, 1, and k equals 3. By analyzing this example step by step, we can see how these optimizations come into play. Let's walk through the example step by step. We start with flip_count equals 0 and the input array nums equals 0, 0, 1, 0, 1. At index I equals 0, nums 0 is 0, so we flip the subarray 0, 1, 2. After this operation, the array becomes 1, 1, 0, 0, 1, and we increment flip_count to 1. Moving to index I equals 2, we see that nums 2 is 0, so we flip the subarray 2, 3, 4. The array now becomes 1, 1, 1, 1, 0, and flip_count increases to 2. At this point, the loop ends. However, the array still contains a 0 at index 4, which cannot be flipped because it falls outside the bounds of any valid subarray. As a result, it's impossible to make all elements 1, so the algorithm returns -1. This example demonstrates how the algorithm applies flips iteratively and detects when a solution is infeasible due to constraints like array bounds. This implementation solves the problem using a greedy approach with an optimized approach for tracking flip intervals. Here's the detailed explanation. 1. Initialization. Flip_count keeps track of the total number of flips performed. Is_flipped is a variable to track the cumulative flip effect at the current index. This optimizes handling of flip propagation. Flip_intervals is an auxiliary array that marks the start of a flip interval. It helps in removing the effective flips that are no longer relevant, i.e., those that end outside the current window. 2. Iterating over the array. For each index I, if it is beyond the range of k, we remove the flip effect of the interval that ends at ik. This is done using the XOR operation, is_flipped equals flip_intervals, ik. If the current bit nums, I, is equal to is_flipped, it means the bit is incorrect, e.g., 0 when it should be 1, and we need to flip it. 3. Handling flips. Before flipping, we check if flipping is feasible. If I plus k greater than n, i.e., the flip would exceed the array bounds, we return -1 since it's impossible to make all bits 1. Otherwise, we initiate a flip by setting flip_intervals, I equals 1, toggling the is_flipped state, and incrementing the flip_count. 4. Returning the result. After iterating through the array, flip_count contains the minimum number of flips required if all bits are successfully turned to 1. If it was impossible at any point, we would have returned -1 during the loop. This approach ensures an efficient solution with a time complexity of O(n), as we only traverse the array once and use an auxiliary array to manage flip intervals. The space complexity is also O(n), due to the flip_intervals array used for tracking. Here, we are implementing the solution for finding the minimum number of k consecutive bit flips in Java. The method min_k_bit_flips takes two parameters, an array nums representing the binary sequence and an integer k which specifies the size of the flip window. First, we initialize the necessary variables. FlipCount keeps track of how many flips have been performed. IsFlipped represents the cumulative flip effect at the current index, which helps us determine the state of the bit. Additionally, we define an array flip intervals to record where flip intervals start, which allows us to manage the cumulative flip effect efficiently. The main logic is implemented in a loop that iterates through the indices of the array. At each index, if the current index is beyond or equal to k, we remove the effect of any flip that has gone out of the current window of size k by toggling isFlipped using the value stored in flip intervals for the corresponding position. This ensures we only consider the flips that are still relevant within the current window. If the current bit, when combined with the cumulative flip effect, is still 0, it means a flip is necessary at this position. However, before proceeding, we first check if flipping at this point would go out of bounds, meaning there aren't enough elements left in the array to perform a full flip of size k. If so, we return -1 as it's not possible to make all bits 1. Otherwise, we mark the start of a flip interval at the current index by setting flip intervals I to 1. We then toggle the cumulative isFlipped state and increment the flip count as we've performed a flip. Finally, after iterating through all indices, we return flip count, which represents the minimum number of flips needed to make all bits in the array equal to 1. In this example, we are given the array nums equals 0, 1, 0, and k equals 1. Our goal is to flip subarrays of size 1 such that all elements in nums become 1. For each flip, a 0 becomes 1, and a 1 becomes 0. If it's not possible to make all elements 1, we return -1. First, we initialize the necessary variables. The size of nums, n, is 3. We set the flip_count, which keeps track of the total number of flips, to 0. The is_flipped variable represents the current flip effect and is initially 0. We also create an array called flip_intervals to manage the start points of flips, initialized to 0, 0, 0. Now, we start iterating. At I equals 0, the current bit is nums, 0, equals 0. Since this value matches is_flipped, it indicates that we need to flip here. We check if there's enough space to perform a flip of size k, which there is because 1 less than or equal to 3. We mark the start of the flip in flip_intervals by setting flip_intervals, 0 to 1. Then, we toggle is_flipped by XORing it with 1, so is_flipped becomes 1. Finally, we increment flip_count to 1. Next, we move to I equals 1. Here, the current bit is nums, 1 equals 1. Since I is greater than or equal to k, we remove the effect of any past flips by XORing is_flipped with flip_intervals, 0. This resets is_flipped to 0. Now, nums, 1, does not match is_flipped, meaning no flip is required. We proceed to I equals 2, where the current bit is nums, 2, equals 0. Again, we remove the effect of any past flips by XORing is_flipped with flip_intervals, 1, but is_flipped remains 0. Since nums, 2, matches is_flipped, we need to flip. We check if there's enough space, and since 3 less than or equal to 3, we proceed. We mark the start of the flip at flip_intervals, 2, by setting it to 1. Then, we toggle is_flipped to 1 and increment flip_count to 2. At this point, all bits in nums have been successfully flipped to 1, so the final output is 2. In this second example, nums equals 1, 1, 0, and k equals 2. We initialize the same variables as before. Here, n equals 3, flip_count is 0, is_flipped is 0, and flip_intervals is 0, 0, 0. Starting with I equals 0, the current bit is nums, 0, equals 1. Since nums, 0, does not match is_flipped, no flip is needed, and we move to I equals 1. At this index, nums, 1, equals 1, which again doesn't match is_flipped, so we don't flip and move on. At I equals 2, the current bit is nums, 2, equals 0. This time, nums, 2, matches is_flipped, so a flip is required. However, when we check if there's enough space to perform a flip of size k, we find that I plus k equals 4, which exceeds n equals 3. This means it is impossible to flip all bits to 1, so the output is -1. In this third example, nums equals 0, 0, 0, 1, and k equals 2. Initialization gives us n equals 4, flip_count equals 0, is_flipped equals 0, and flip_intervals equals 0, 0, 0, 0. At I equals 0, the current bit is nums, 0, equals 0. Since this matches is_flipped, a flip is required. We check if there's enough space, and since 2 less than or equal to 4, we mark the start of the flip at flip_intervals, 0, by setting it to 1. We then toggle is_flipped to 1 and increment flip_count to 1. At I equals 1, the current bit is nums, 1, equals 0. This time, since I is not yet greater than or equal to k, no past flip effects are removed. Nums, 1, still matches is_flipped, so another flip is needed. We mark the start of the flip at flip_intervals 1 by setting it to 1, toggle is_flipped back to 0, and increment flip_count to 2. At I equals 2, the current bit is nums 2 equals 0. Since I is now greater than or equal to k, we remove the effect of the flip at flip_intervals 0 by XORing it with is_flipped, which updates is_flipped to 1. At this point, nums 2 does not match is_flipped, so no flip is needed, and we move on. At I equals 3, the current bit is nums 3 equals 1. Again, we remove the effect of the flip at flip_intervals 1 by XORing it with is_flipped, which resets is_flipped to 0. Since nums 3 does not match is_flipped, no flip is needed. All bits are successfully flipped to 1, and the final flip_count is 2, so the output is 2. To analyze the time complexity of our solution, we begin with the outer loop. This loop traverses each element in the nums array exactly once, making its contribution O(n), where n is the length of the array. Within this loop, we also perform a constant time operation to update the is_flipped variable when outdated flip intervals are no longer relevant. This involves a simple XOR operation and accessing the flip_intervals array, both of which are O(1). Additionally, for each element, we check whether a flip is required. If so, we update the flip_intervals array and toggle is_flipped, both of which are also O(1) operations. Since the number of flips is bounded by n, the total time complexity remains O(n), as the loop runs in linear time and all operations inside it are constant time. Now, looking at the space complexity, the external input array nums does not contribute to the algorithm's additional space usage, as it is provided externally. The main contributor to additional space is the flip_intervals array, which has the same length as nums, resulting in O(n) space usage. Beyond this, the algorithm uses a few simple variables such as flip_count and is_flipped, which only require constant space, O(1). Therefore, the overall space complexity is dominated by the flip_intervals array, making it O(n). Let's analyze the best, average, and worst cases for this algorithm. In the best case scenario, no flips are required because the initial array already satisfies the condition. Here, the loop still runs through all elements, resulting in O(n) time complexity, with O(n) space complexity due to the flip_intervals array. In the worst case, every bit in the array requires a flip. Even then, the algorithm performs each operation in constant time, keeping the time complexity O(n). The space complexity also remains O(n), as it depends on the flip_intervals array, regardless of the number of flips. For the average case, the algorithm involves linear traversal with some flips occurring, but the time and space complexities are still O(n) for the same reasons. Finally, let's compare this optimized approach to a naive solution. The naive approach would involve directly flipping the next k elements every time A0 is encountered. For each flip, up to k elements would be modified, leading to a worst-case time complexity of O(n*k). However, the space complexity would remain O(1) if no additional data structures are used. In contrast, the optimized solution avoids modifying elements directly by using the flip_intervals array and maintaining a cumulative is_flipped state. This reduces the time complexity significantly to O(n), although it introduces an O(n) space requirement due to the flip_intervals array. The big O justification for the optimized approach is straightforward: the outer loop runs in O(n), with constant time operations inside, making the overall time complexity O(n). The space complexity stems from the flip_intervals array, which requires O(n) space, while all other variables require only constant space. When working on this problem, there are a few common mistakes to keep in mind. First, forgetting to handle edge cases for the value of k can lead to significant issues. For example, if k is larger than the length of the array, the algorithm might attempt to flip bits that don't exist, causing runtime errors. Similarly, if k is 1, the flipping logic might not be optimized, leading to unnecessary operations. Another mistake is modifying the input array directly while iterating through it. This can lead to unpredictable behavior, especially since flipping bits changes the array and impacts subsequent operations. A better practice is to use a temporary array or maintain a separate state to avoid overwriting data prematurely. Additionally, inefficient flipping implementations, like flipping the same subarray multiple times in overlapping windows, can significantly increase the runtime. For instance, in a brute force approach, repeatedly flipping overlapping subarrays can lead to n² time complexity. Lastly, overlooking performance trade-offs is a critical issue. While brute force might work for smaller arrays, it will time out for larger inputs, such as when the array size is 10 to the power of 5. Optimizing with techniques like sliding window or greedy methods is essential to improve efficiency and reduce redundant computations. Another common oversight is failing to validate edge cases where the array consists of all 0s or all 1s. For example, if there are no 0s to flip, or the array is entirely 0s, some implementations might produce incorrect results or even enter infinite loops. These edge cases are critical to handle to ensure the robustness of your solution. On the interview side, recognizing patterns and problems is key. Many flipping or subarray transformation problems benefit from sliding window or greedy approaches due to their ability to optimize time complexity by avoiding redundant operations. Testing boundary cases is also essential. Interviewers often assess your solution with extreme inputs, like empty arrays, single-element arrays, or arrays with uniform values. It's important to rigorously validate your implementation in these scenarios. Additionally, you should be prepared to discuss the trade-offs of your chosen approach. For example, why you opted for a greedy algorithm instead of a brute force one, and how that impacts both time and space complexity. Lastly, clear communication is vital. Explaining your thought process, particularly how you handle edge cases and optimize your solution, demonstrates a thorough understanding of the problem and the reasoning behind your approach. This problem is closely related to other flipping and subarray optimization problems, which can help you recognize patterns and refine your approach. For instance, LeetCode 487, max consecutive ones 2, involves flipping at most 1 0 to maximize the number of consecutive 1s. Similarly, LeetCode 1004, max consecutive ones 3, expands on this idea by allowing you to flip up to k0s. These problems share similar strategies, like sliding window, to optimize the solution. Another related problem is LeetCode 1423, maximum points you can obtain from cards. While the context is different, the optimization strategies involve sliding windows and dynamic adjustments, making it conceptually similar to the techniques used here. Familiarizing yourself with these problems can deepen your understanding of how to handle overlapping subproblems, efficiently manage constraints, and identify the most suitable algorithmic approach for a given scenario. To approach this problem effectively, there are several alternative strategies worth considering. The sliding window approach is a powerful technique where you track the state of 0s within a window of size k and dynamically adjust it to minimize flips. This reduces the time complexity to n, though it may require additional space for bookkeeping. Another highly efficient method is the greedy approach using a deque. This method tracks the indices of flips and ensures flips are performed only when absolutely necessary to maintain the desired state. While this approach is more complex to implement, it offers significant performance benefits for larger inputs. Lastly, an optimized brute force approach involves maintaining a flip count and applying flips lazily during validation rather than flipping all bits in a subarray directly. While simpler to understand, this method is less efficient than sliding window or greedy techniques. Each of these approaches comes with trade-offs in terms of complexity, runtime, and space requirements, so it's important to choose the one that best fits the problem constraints and input size. Great job following through the solution. To summarize, we tackled the problem using an efficient approach that optimized both time and space complexity. Remember the key concepts we discussed, and keep practicing similar problems to sharpen your skills. Thanks for watching. Don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!